Hi guys, welcome back. So you might have given the likes for the page so that you will be getting the updates on the page. But I'm not sure you're getting the updates, so that we have updated the cover photo. So that's how to get the updates from the page. And the instructions are there. Just go to it and make sure that you get the updates on the page. So okay, where were we the last time? It was a long time back. So okay, the previous post I have raised some questions about why do we remember Newton's third law, but not that familiar with the first and second law. We don't. Most of the people don't remember the first and the second law, right? So why are we much familiar with the third law, and why don't we remember the first and second law? Actually, the third law is quite obvious and a simple thing we quietly see around us. For every action, there is an equal and opposite reaction. So it is the quite obvious thing, so that we remember. So why don't we remember the first one? Because isn't it obvious, or it's something that doesn't have to be a law? That means it's wrong or something else. So okay, let's see what does Newton's first law state. So it states something like for any object which is in its state of rest or on an uniform motion, continue to be in its state of rest or uniform motion unless it is compelled by an external force. Okay, that's it. So let us separate this into two things. Actually, let us say first we will split the first law into two. So an object continue to its in state of rest unless it is compelled by an external force. So it is so good. It's okay. It's okay. So okay. What's the second law? An object which is in uniform motion continue to be in uniform motion unless it is compelled by an external force. Okay. Okay. We will try it again. Okay. Why does this thing doesn't go in an uniform motion? So it initially had some uniform motion. It doesn't have that uniform motion till the end. So is Newton's first law wrong? So okay, normally this is the problem what we face. We doesn't see what Newton sees in his first law. We saw the third law as Newton saw that, as Newton had as what Newton had in mind while he was writing that law. But while writing his first law, he had something in mind, but we don't perceive the same thing. So okay, how to perceive it? So what he explains is unless that it is compelled by an external force. So is there any force compelling this object to stop? So yes, there is. It is the friction between my hand on the object. This is compelling this force. Okay, so as to give you some better understanding, we have some animations. Okay, let's watch the animations and let's get back.
Here is a wooden apple resting on a countertop. Before seeing anything else, you've probably made a number of assumptions. We rightly think that the marble counter is heavy and rough, and that the apple is smooth and light. Say we plan on giving the apple a shove to the right. We all have an idea of how the apple will slide and stop. And thanks to our intuition, we can make predictions like this on a moment-to-moment basis without much effort at all. But what if it were possible to remove everything that our intuition is based on? What if we could remove all the air in the room, which can cause air resistance? Remove all the friction from the ground and walls, and remove the force of gravity. Now if we pick the apple up and let it go, it won't move anywhere because there's absolutely no forces acting on it. If we bump the apple now, would it ever stop moving? The truth is, once we give the apple a bit of velocity, it stays at that velocity, moving in a straight line until it's bumped again. This isn't just an imaginary experiment. It turns out that this is exactly what happens in outer space. Newton's predictions are now known worldwide as Newton's 3 laws of motion and are used when dealing with anything that moves, from cars and trains here on Earth to spaceships that fly to the moon. At the start of the video, we asked the question, what causes an object to speed up? Newton answers this question in his first law of motion. An object with constant position or constant velocity will remain at that position or velocity unless acted upon by a net external force. Well, this is just reiterating what we already realized. The only thing that could cause our apple to accelerate was a force. So what is the next logical step in understanding why things move? If we now know that a force causes acceleration, we might also wonder how much acceleration we can get from a certain force. The answer to this is actually Newton's second law of motion. F is equal to m multiplied by a. This means that if you want to speed up an object by a certain amount, you will have to adjust your force depending on the mass of the object. Heavier objects need stronger forces. Let's look at what this math means in real life. There are 3 variables in the equation, so we'll look at 3 examples, each with one variable held constant. But before we start, let's bring back gravity. Okay, first let's hold the mass constant. Let's bring in 2 toy blocks of the same size. This part is pretty intuitive. If we gently push the first block, it'll accelerate slowly. But if we push the second block with twice the force, it's going to accelerate twice as fast. What if we were trying to push something much heavier, like 2 large masses? Now our robotic arm has to push at 100% of its strength to move these objects. And when we push the heaviest mass, it's a big struggle. But when we push the smaller heavy mass, even though we're pushing with the same force, we can make it move faster because it's lighter. In our third experiment, let's drop a hammer and a feather from the same height at the same time. What does your intuition tell you will happen? Most people imagine the hammer hitting the ground first, because it's heavier, so it falls faster. Let's try it out. They hit the ground at the exact same time. Amazingly, humans have actually done this experiment on the moon, and it turns out that our predictions are completely correct. Let's look a bit more at this third experiment, since its results are a bit unexpected. If the acceleration of the hammer and feather are the same, then what does that tell us about the forces and masses? Well, we know that the hammer has more mass than the feather. So that means that for the math to work out, the force of gravity on the hammer must be more than the force on the feather. So we know from Newton's second law that the hammer and the feather fall at the same speed, because even though the hammer is pulled with more force, it also has a greater mass. So in the end, the ratio of force to mass is the same for the 2 objects. This is why they fall at the same rate. What we have just stumbled upon is actually a very important distinction in science. The force of gravity acting on an object is known as its weight, which is not the same thing as the object's mass. You can think of mass as something that belongs to an object no matter where it is, whereas the weight of an object changes depending on the gravity of the planet that you happen to be on. In outer space, your weight would be 0 newtons. But since acceleration is constant at 9.8 meters per second squared on Earth's surface, we can use the force of gravity is equal to the mass times the acceleration of gravity to quickly find the weight of an object from its mass, or vice versa. For example, the weight of a 10 kilogram mass on Earth's surface is 10 kilograms multiplied by 9.8 meters per second squared, or 98 newtons. So now let's look back and try to explain why our intuition was wrong. What goes on when there is air resistance that makes the feather fall more slowly? Let's look at the feather on its own to start. We just found out that the feather has a small weight because it has a small mass. So this means that the force of gravity pulling on the feather is relatively small. So let's draw a small arrow to represent the force of gravity acting on the feather. What other forces are acting on the feather? Well, in a vacuum, gravity would be the only one. But with air resistance, there is actually a second force acting on the feather, in the opposite direction to the force of gravity. For a hammer and a feather, the force of air resistance is nearly equal. But since a hammer has such a larger mass, the hammer barely notices this small force of air resistance. For most calculations in high school physics, we deal with objects that are large and fairly heavy, so you can usually ignore air resistance. But for a feather, it makes all the difference. The analysis technique that we have just used is one that you will use all the time from now on. The use of arrows to represent all the known forces acting on a single object is called a free body diagram. For problem solving in physics involving forces, you will almost always start by drawing one of these. On that note, we are now completely ready to tackle Newton's third and final law. So far we have answered our two biggest questions. First, what causes an object to accelerate? And second, by how much does the object accelerate given a certain force? It might seem like we have asked the two most important questions, but Newton thought of one more question to answer, which most people might not have thought of. The first two laws are centered on an object that is accelerated by a force. But what is providing the force in the first place? Newton's third law is that there is no such thing as a lone force. All forces come in pairs. In technical language, for every action force, there is an equal and opposite reaction force. Let's look at some examples. When a robotic arm pushed on those masses as hard as it could, the masses were actually pushing back on the robotic arm with the same force. When the earth pulled on the hammer as it was falling to our studio floor, the hammer was actually pulling back equally hard on the earth. But since the earth is so large, we don't notice the earth accelerating towards the hammer. And as you sit in your chair pushing it down with your weight, it pushes back on you with an equal force. You wouldn't even be able to walk if Newton's third law weren't true. When your shoes push back on the ground pushes forward on your shoes, and this is the only reason you are able to walk forward. Okay, let's take a breather.
Okay, hope you have enjoyed it. Okay, see you on the next post, and thanks for watching. I forgot something. Okay, the next question, right, for the next post. Okay, we'll have this one. So, what is heat? Just think about it. We'll catch you on the next post. Thank you.